As Sergey said, my name is Colin Wilson. I'm a HBTC at SharkNet out of the University of Guelph. Today I'm going to be talking about Fully Sharded Data Parallel, which is a tool within PyTorch that we can use to train very large models. So to get started, we'll talk about why we might need this tool, Fully Sharded Data Parallel. And then we'll talk about what it is, which requires a brief introduction to the standard data parallelism library in PyTorch, distributed data parallel. And that will allow us to kind of contextualize fully sharded data parallel and kind of understand kind of how it works under the hood better. And then we'll look at a code recipe, which is really more of an ingredient list for what you need to implement FSDP in your model training. If you're familiar with distributed data parallel, a lot of this will look very familiar. And then we'll look at some extra options that you can use to customize the configuration of fully sharded data parallel, including the sharding strategy and some other optimizations. And then we'll look at a few demo runs to kind of see how FSDP might be saving you memory footprint and what the cost might be and how those two, how the cost benefit analysis works out. So let's get started. Why do we need fully sharded data parallel, which from now on I'll be calling FSDP? The trend in deep learning has been towards larger and larger models as hardware improves. And then FSDP allows one to train models that are too large to fit into a single GPU. So that's our main use case. And this has allowed the proliferation of models that are larger than even the state-of-the-art GPUs, which for us as researchers means when we're interacting with these models and kind of doing experiments with them, we also need to know how to do this FSDP training with them. It's also used in many third-party packages like PyTorch Lightning and Accelerate from Hugging Face. So if you're using those packages and want to look at training larger models, you'll be likely be getting into FSDP. And I encourage you to do that. I've used it in Accelerate and it's quite easy, but it does take some configuration. And I think understanding how the underlying tool works in PyTorch will help you with configuring in these third-party packages if you choose to do so. So what is FSDP? In quote unquote, normal PyTorch data parallelism, that is distributed data parallel or DDP for short, each GPU gets a clone of the model and the optimizer. And then each worker gets a batch of data, and then gradients are synchronized using an all reduce across them. So a batch of data comes into a rank, goes through the forward pass through the optimizer, backward pass, and then the gradients are all accumulated and synchronized across all of the ranks so that our models stay in sync as we move through batches of data. So FSDP is also data parallelism, except that the model parameters, the optimizer states, and the gradients are sharded across DDP ranks. In other words, each rank only keeps a subset of the parameters, the optimizer states and gradients, and instead of keeping the entire set throughout training. And that means that FSDP has a smaller memory footprint than DDP, and that is what allows you to train larger models. But this trade-off is not free. We're trading memory footprint for communication cost. So kind of, a picture here is we're wrapping subunits of our model in FSDP instances, and then each of those are getting sharded across DDP ranks. So broken up into pieces, and our GPU is only storing those pieces during training. And that might seem odd. How does this work? Well, if we look at the workflow, what happens is the we get to the say the first FSDP instance. So in this basic network, our convolutional neural network, we've put our convolution and pooling layers into an FSDP instance. So the across all of our ranks, they'll gather all of the parameters associated with that instance and load them onto the GPU. So we're doing lots of inter GPU communication here. So now each rank has all of the parameters for that instance, not the entire model, but for that first section of our model here. Then we do distribute our data like we would in DDP to each of the ranks and do our forward pass. And after the forward pass, the full weight set is freed up. So we're no longer holding all of the weights for that full FSDP instance. We're still only holding onto the shard that belongs to our rank. And this proceeds through all of the instances in the forward pass. And then we go back through the backward pass. And this happens again. We gather all the shards for the FSDP instance we're looking at, do our backward pass, and then we do something called a reduce scatter to distribute the gradients. And then we free the full weights again. So all gather, reduce scatter. What does all this mean? So on the left here, we have an all reduce, which is what happens in DDP. We have each of our ranks, A, B, C, D, working on different data. So each of them gets their batch gets split up along the ranks. Each of them operates on that data, calculates different gradients, and then we reduce and synchronize those gradients across all of the ranks. So all of the updates are the same across all of the ranks, and our models stay in sync. What happens in FSDP is we start with this all gather. So what we're looking at here is this kind of vertical rectangle is a FSDP instance. And then A, B, C, and D are the shards distributed across all of the ranks. So the first thing we do is we do an all gather. So now all the ranks have all of the shards. So each of them has a complete FSDP unit. Then we do the same thing we do in DDP. We run our batch through that unit, not through the whole model, but through that unit. And then later do that again in the backwards pass, upgrade our gradients. So what we end up with is a gradient set for each of the shards on each of the ranks. And then now we distribute those gradients, but instead of distributing the entire gradient set, we just distribute the gradients for the shard that belongs on that rank. So we're moving less gradients around. We're keeping less gradients on the GPUs for a shorter amount of time. And having done all this, we save some memory space, but at the cost of a lot of communication. And this kind of complicates the picture for figuring out our memory requirements. So kind of the worst case we're looking at is what is the size of the largest unsharded FSDP unit? And what is the size of the unsharded gradients for that unit? What is the optimizer state in that unit? And then we also are still keeping all of the shards on the other units still on that rank. And then the activations. So really our savings is coming from these 3 bits. Instead of keeping the entire model, the entire optimizer state, and the entire set of gradients, we're only keeping a subunit and then shards of all the other shards of the other units. And this is how we can kind of squeeze a model down into a smaller memory footprint. But this, as I've said many times, and we'll see it demonstrated further on, it comes at a very high communication cost. But when we can't fit a model into a single GPU, this is the best we can do. We can either make the model smaller, which is not kind of the goal we're working towards, or we have to come up with these other kind of clever ways of handling those large models and reducing their memory footprint. So, code recipe. We have our ingredients. The first ingredient is a working model with a training loop, kind of all that boilerplate code that if we've worked with PyTorch before, we've seen it many times. As soon as you have that, then you can think about working on making it distributed, but kind of make sure you have that basic skeleton, the basic framework in place before you think about applying DDP or FSDP. And then the next thing we need is a distributed process group, which is kind of the back end that coordinates the communication among the GPUs. Then we need to set up our distributed data loading with a distributed sampler. And then we need to add in our FSDP wrapper with options. So coming from a working model with a training loop and all that stuff set up, these three, distributed process group, distributed data loading with a distributed sampler, and an FSDP wrapper are the only kind of real code modifications that you have to make. And we'll work through each of these step by step. So, distributed process group. Like in DDP, you need to initialize a process group to coordinate the communication among the ranks. So, we use the dist. We use torch.distributed to do this, and the function is init process group. Here we're using the backend NCCL, but you can also use glue. And this is exactly the same as we would have in DDP. Now, if we use this init process group also takes some arguments, rank and world size. But if we use torch run to launch our training scripts, then world size, rank, and local rank are all handled by torch run and stored in environment variables, and torch.distributed will kind of figure that out for you. If you're going to launch your script with, say, something like srun, then you need to kind of figure out local rank and rank yourself in your Python script and pass those to distributed init process group on your own. Yeah, and then the next thing we need is distributed data loading with a distributed sampler. So like in DDP, you need to initialize the process group to coordinate communication between the ranks. So, we have to import our distributed sampler. We have our data set. In this case, it's ImageNet, the training set specifically. You set up your sampler, which takes your data set, also your rank, and the number of replicas you're going to be working with, which is the same as your world size. And then we're also setting it to shuffle. And then in your data loader, you just have to pass this distributed sampler in using the sampler argument and set shuffle to false, since these are kind of mutually exclusive options. And that's it for setting up distributed data loading. You have your backend process group running. You have this distributed sampler in your data loader, and that will handle distributing the data to your ranks in that way. An important thing to note here is the batch size is the batch per rank. So let's say your batch size is 2, and you're running across 4 ranks, then your effective batch size is actually 8. So that's something to be aware of. Yeah. Okay, so finally we get to the FSDP wrapper. So there's a bunch of options you can import from FSDP, and we'll kind of go over some of these later. But one key thing that you need is some sort of auto wrap policy. And this just dictates how your model will be broken up into those FSDP units. And then in your code, you can set your CUDA device to be the local rank, set up your auto wrap policy. And then here we're using the ResNet model, we're compiling it, and then we're wrapping it in FSDP. And that takes the auto wrap policy and also the device ID. And since we've set the device to be our local rank, we have the right GPU matched up with the right process. This will move the device. This will move the model to the correct device and initialize it there. And then we also pass it the auto wrap policy. So in total, what this kind of implementation here is doing is it's taking the model, applying the auto wrap policy, and then moving it to the CUDA device and initializing it there. So Wes, I see. Will this particular code block work with non-CUDA GPUs? So PyTorch does have support for ROCm. I don't know specifically how this will change for that setup. I imagine instead of using torch.cuda, you'll use the whatever the syntax is for the ROCm setup in Torch. I know that is kind of experimental. It's not like fully developed their support for ROCm, but it is there. So you'd kind of have to look at the documentation to see how it changes. I don't know if FSDP is actually supported for ROCm yet. Yeah. Apple Silicon. Yeah, it's same thing for Apple Silicon. You'd have to look up to see how it works, though a multi-GPU setup with Apple Silicon would be kind of unique. Okay, so going back to our simple convolutional network, the picture we had before is we had the first unit is the first bit of our network, and then our second unit is the fully connected layers that we use for classification at the end. But the auto wrap policy we're using here is called a size-based auto wrap policy, and it takes an argument called min-num params, which is the minimum number of params required to wrap the module. So the way this will work is FSDP will traverse through kind of the tree of your model. If you have it, broken up into classes, it will traverse through the various layers and classes that you have that make your model, and it will look at the number of elements, the number of parameters essentially that make up that submodule. And in this case, it'll say, okay, the number of parameters in this subunit is greater than 1,000. This is going to be its own FSDP unit or instance. And you can set this to be recursive or non-recursive. So we'll kind of see more options for customizing this later. But essentially, the way the size-based auto wrap policy works is it looks at a submodule in your model. If it meets this minimum number of parameters, it wraps it in its own FSDP unit. This is a tunable parameter, and it's very important that you kind of do some experimentation with this, because it essentially, if you're using a size-based policy, it dictates exactly how much of the communication memory trade-off you're going to be looking at. And for some models, if you set this too small, you're going to end up with too many FSDP units, and you're going to be doing way too much communication among your GPUs, and it won't really be worth the memory savings that you're looking at. So back to our picture. Here we're using a size-based policy. A good thing to do after you have kind of wrapped your policies, you can print your model. It's just, print model, and it will show all the different layers in your model, and you'll be able to see what gets wrapped in Fully Sharded Data Parallel. And we can see in this case, we only have 2 FSDP instances. We have the greater one that wraps the whole model, and then the first fully connected layer gets wrapped into its own unit. Everything else is bundled into a single FSDP unit, and then this layer is kind of on its own in its own unit. So really, our picture looks more like this. We have our Unit 1 encompassing the entire model except for this layer, and then in Unit 2 is that layer. So you can see how, you might want to work on being more clever with how you're wrapping your model in FSDP units, because in this case, we're jumping to Unit 2 and then having to reload Unit 1 again after to do the final layer. So we're kind of doubling our communication cost, and it might be something, do I want to wrap this whole thing, my entire fully connected network, into something that can be its own FSDP unit? And that's something you can do. You can do these very customized wrapping operations so that you end up with kind of a more optimized setup of FSDP units. So you can create your own wrapping policy or use one of the pre-made ones. There's specific ones for transformers. There's a specific class for customized ones. A auto wrap policy is just a callable, and it requires to take a module. You need to set the recursion a recursion argument. So this would be whether or not it proceeds into a module to look at the submodules inside of it to see if they should be wrapped, or if it just stops at that stage and wraps the whole thing. And then for this one, this custom auto wrap policy is essentially the size-based auto wrap policy. We also have minimum number of params. And then there's also this non-wrap num elements, which is just kind of FSDP keeps track of how many elements aren't wrapped in the current module. So the return here is it compares the number of non-wrapped elements in the unit with the minimum number of parameters. And if it's bigger, it wraps it in a unit. So that's kind of the bare recipe for creating a custom policy. But there's also a class for custom policies in which you can do all sorts of interesting things and get kind of like really down in the nitty gritty, which is likely what you would have to do with a more complicated model. If you have a custom model, you're going to have to be using custom options to optimize FSDP with it. So let's look at the options. A major option we need to talk about is the sharding strategy. So you can go with full shard, which is the default, in which case the parameters, optimizer states, and gradients are all sharded. You can also go for the shard grad operation, or shard grad op, sorry. And that in that case, the optimizer states and gradients are sharded during computation, but the parameters are sharded outside of computation. Now, what that means is, in kind of our flow diagram that we had before, after we're done the local pass, forward local pass, we're not freeing the full weights. We kind of hold on to that unit until we get to the backward pass and then release it. So we're just kind of getting rid of this step. And you can see, very much how this would affect your memory. Now, kind of at the end of your forward pass, you've essentially gathered up the whole model again. So, how this works is, kind of, you wouldn't necessarily want to use this on an entire model. You can apply different sharding strategies for different subunits. And this is kind of, looking at more interesting ways of managing memory, that memory and communication trade-off. Then there's no shard, which is basically DDP, except the optimizer states are updated locally per rank. So you'll actually get divergence of your optimizers, I believe, among the ranks. So your models won't be exactly the same across ranks. And the next option, which is another interesting option, is hybrid shard, where you apply full shard within a node and then replicate the parameters across the nodes. So now we're talking about like a multi-node, multi-GPU setup. We do full shard within a node, so that all of the communication or the major communication overhead we're paying for the smaller memory input all happens within a node where the communication is faster and more efficient, and then replicate parameters across nodes. So you can think of this as like FSDP within a node and DDP across nodes. And then the last option here is hybrid shard 02, and that applies the shard grad op within a node and then replicates parameters across nodes. Okay, so just for kind of example of how this works, to use the sharding strategy, you have to import sharding strategy from FSDP, and then pass the option into the sharding strategy argument, and it's just sharding strategy dot the option that you want to use. So you could use, shard grad op, as we show here. The default would be full shard, hybrid shard, and that sort of thing. Some other optimization options are backward prefetch. This is on by default, and this says whether FSDP starts gathering the shards of the next FSDP unit during computation of the current unit. By default, this happens, but it can be disabled to further trade communication for memory. So the how this is kind of helping to begin with is it's overlapping that communication time with our computation time. But if we're really constrained on memory, we might not want to be loading in the next unit while we're working on the current unit. So you can turn this off, and that will help. That will help with the memory footprint. So this is again like really now we're we're desperately really squeezing our model to try and fit it in and really paying the price in communication for it. There's also mixed precision options. This is a whole other, bag of very customizable options for you can go like layer by layer, or like unit FSDP unit by unit can have different mixed precision policies. So different layers can be using lower precision for the gradient communication versus calculation, that sort of thing. And then the final option is CPU offload, in which we can offload parameters to the CPU when not in use in computation. If I go back to this picture here, it shows kind of how CPU offloading works. Shards, instead of being stored on each rank, they're stored kind of off the GPUs in the CPU memory, and then we load them from CPU. And this, again, now we're looking at communication between the CPU and the GPU, which is even slower than our inter-GPU communication. But we're, really squeezing our memory constraints there. Okay, so let's look at some demo runs. So our first one is just very simple. It's just ResNet 152 on ImageNet. ResNet is just built into Torch Vision. You can import the various size ResNets fairly easily. I did this on the H100s on Gram, which are available. And I did several runs with different sizes in that wrap policy. I used a size-based wrap policy. I used PyTorch Profiler, which was the subject of my last colloquium. So if you're interested in that, I'd encourage you to look back at that and kind of see all the different options for PyTorch Profiler and what's available to use. And in this case, I used the TensorBoard trace handler to generate analysis because it gives me a nice kind of overview and picture that I can flip through and show you guys how our memory and communication trade-off is working. I will note I use the glue backend. That seems to be that the NCCL that comes bundled with PyTorch needs to be updated in our wheels for it to work on these new nodes. So stay tuned for that. That's a work in progress. So I am using the glue backend, so our communication cost is likely actually higher than it would be if we're using NCCL. Okay, so if I flip over to TensorBoard here, I can see I'm using DDP with ResNet 152. This is kind of our baseline. Um, this model does fit onto a single GPU, so keep that in mind. We have a GPU efficiency of 82.35%. And actually, we're not even using the maximum batch size that would fill up this GPU, so we can push this higher if we wanted. Our average step time is 349,000 microseconds. And we're, this efficiency is where the GPU kernel is taking up 82.35% of the time that we're that we're that we're doing computation. You can see the step-by-step breakdown. Each of these is a GPU. I ran this for 5 time steps from iteration 15 through 20. And you can see a nice breakdown of what is what our communication or what's being spent on. The communication here is that distribution of gradients. So there is a bit of communication overhead with DDP, as we should be aware of. If I move on to this guy, this is ResNet wrapped in a single FSDP unit. So this is kind of not really saving us any memory at all, but the communication cost is extremely high. And you can see, the jump. Now we're spending most of our time doing communication because we're transferring model parameters around all the time and gradients and optimizer states. And our efficiency is less than half is what we expect. But we want to be smarter with our kind of configuration. This is no auto wrap policy whatsoever. We're not really saving anything by doing this. So if I go here now, this is essentially the same run here, but if I go to this one, this is our maximally wrapped ResNet. So essentially every layer is wrapped in its own FSDP subunit. You can see now the communication is high, but also our CPU execution is very high because now the coordination of this communication is coming into play, and our GPU utilization has dropped way off. If we look at the memory here, we're sitting at, just over 44 gig. And if I go back to DDP and look at memory, we're not that much higher. We are saving a little bit, but not enough to be meaningful difference in this case. If I go back to our wrapped models, so this was kind of our maximally wrapped. So every layer is wrapped in an FSDP subunit. And then if I kind of go up, you can see our utilization is climbing up. We're using fewer subunits. Continuing on, the trend goes up as we wrap fewer and fewer subunits. And then once we get to, higher, if I go 10 here, I'm only using 3. I'm getting close to the GPU utilization that I had with DDP. But there's this extra communication cost, and our average step time is almost twice as long. So you really need to think carefully about when you want to use FSDP. In this case, we're looking at a model that does fit on a single GPU. Maybe it doesn't have the right architecture to maximally use FSDP. Maybe we could take more time considering carefully how to wrap our layers and what kind of like the most efficient way of doing that would be to kind of maximize the trade-off. Because right now we're trading memory for a lot of communication, but not very much memory compared to what we would hope. So if I go to memory here, so maximally, so yeah, just under 44 for for kind of maximally wrapped. So this would be like our best case memory footprint you would expect. And then if we kind of go down to 3 units, then we're up over 44. So we're really not saving that much memory by doing this. One interesting thing from the memory plot is that you can see how this is proceeding. We're loading our first subunit, and then there's this wait time while we're doing more communication, getting our next subunit, the next and next, and then starting gradient computations, and then that goes down. We can look at how the distributed. This is a nice window too, kind of showcasing the TensorBoard integration here. If you look at distributed, it'll show you kind of breakdowns of the computation communication, how much of overlap there is. The more overlap, the more communication cost you have, the more you want it to be taken up by this overlapping, because that means you're computing and communicating at the same time. So there's all sorts of interesting things that we can look at here. You can even open up, let's go open up the trace, which is the same trace that I showed in my colloquia. You can look at the traces within this TensorBoard extension. So that's just kind of an advertisement for this way of looking at using PyTorch Profiler more than being relevant to FSDP. But I'd encourage you to do this kind of profiling, kind of dig down into what's going on, so that you can kind of optimize and make your training as efficient as possible. Okay, so let's look at our next example. I also used a vision transformer on ImageNet. It's a modified implementation from this blog shown here. Again, I'm using Graham H100s, and this time I'm using the transformer auto wrap policy, which is another built-in auto wrap policy in PyTorch. And it's expanded to be very large. So on the H100s, it only took a batch size of 2. Now, the way a vision transformer works is, like with language, you have a sequence of words, and then you kind of flatten them and send them through your transformer. But with an image, it's like, what's a sequence in an image? Well, you break it up into patches and then send those patches in as a sequence, and that requires your patch and position embedding, and then you feed that into your transform. And this example is really more illustrative of how this auto wrap policy works, and we'll kind of get into that. So this auto wrap policy takes a transformer layer class. So you have to know what the transformer layer is in the model that you're working with and give it the class name. So you have to import that class name from whatever model you're using. In this example, it's called transformer encoder. And then pass this as an argument to transformer layer class in your transformer auto wrap policy. And that will mean that the auto wrap policy is every instance of that class in your model gets wrapped into an FSDP unit. And then, so you can imagine in this case, every layer in our transformer encoder will be its own FSDP subunit, and then everything else, the patch and position embedding, our multi-attention head, and our fully connected network will be in their own FSDP subunit outside of that. And then, so if we're looking at a very deep model here, which, here we're looking at 100 layers. This is the way it was originally written. Our transformer encoder is just a sequential layer of these 100 layers. Now we're getting into that situation we saw with ResNet, where we're going to be wrapping a lot of layers into their own units, and our communication cost is going to explode. So maybe a smarter way to do this is to implement another class in your model called a transformer block that groups those layers together into blocks of layers. So instead of having just one sequential of all of the transformer encoding layers, we have these blocks. And that way we can divide them up into to bigger FSDP subunits and use the transformer block instead of the layer in our transformer layer class. And that will help with that communication overhead. One big thing to note about these auto wrap policies, and if you're doing custom policies, is if you have layers with shared weights, they have to be in the same FSDP subunit. So that's a good thing to take note of and be aware of. Okay, so if we do this, let's look at DDP for this vision transformer. This is a model or a memory profile output by PyTorch Profiler, which you might recognize. And it has a nice breakdown of what is coming from where. And in this case, what we see is our optimizer states and our parameters, our gradients, and kind of the other overhead are very small compared to our activations. Our activations are really dominating the size of this model. With DDP, we're at over 50 gigs max memory in these two iterations. Kind of profiling these runs is very intensive. I can only do 2 iterations, otherwise the profiles became unmanageably large. And if we look at FSDP, we're saving 3.5 gigs by wrapping. This is using transformer blocks, I believe, using 2 or 3 block or 5 blocks here. Actually, you can see it. So each of these is an FSDP unit. You can see the communication time. But again, we're being dominated by the activations. You can see the flow of parameters in and out of memory, which is interesting. So this is a nice view of what's going on. You can see how the gradients are flowing in and out, compared to in normal DDP, the gradients, accumulate and then drop out as they're applied at the end. Whereas here, the gradient footprint is quite a bit smaller. So it really kind of depends on your model. If you're being dominated by activations, and you're not going to be able to squeeze so much out with FSDP compared to other methods. But if you're in a situation where your gradients, you have lots of gradients, or your parameters are dominating, then FSDP will save you a much higher memory footprint than not using it. So now we can kind of see what sort of models and what sort of memory profiles would benefit more from FSDP. I've also included the throughput here, so you can see the extra communication time. So is 3 gigs worth the all the extra 30% of time per batch? Probably not. But if we're 3 gigs away from being able to stick an extra example in our batch size, maybe. If we're going from like 2 to 3, maybe. So there's all these considerations, and this is kind of the simplest and least customized configuration that you can make with FSDP. It really is about getting down into the nitty-gritty details of your model and smartly optimizing the way it's being wrapped, what operations are being sharded in each wrap, and that sort of thing. There's a whole ocean of possibilities to go through. So we're likely going to be getting into a two-parter with this one. So as I said, the activations are really the limiting factor on memory in this model. And a solution for that is activation checkpointing, which is a further trade-off in computation and communication. And it's very often combined with FSDP. So we'll likely be talking about that in the future. So stay tuned for that. Final thoughts here. In general, you can use if you can use DDP, you should. The communication trade-off is too much for models that fit on a single GPU. You need models that really kind of expand out of that and can benefit from this memory crunching. You should reserve your use of FSDP for those cases where it's impossible to fit a model on a GPU, a single GPU. Um, it has a very large array of configurations, and it requires lots of tuning and experimentation to find the best footprint throughput. But if you're in a situation where you can't fit on a single GPU, this is kind of the way you have to go. You can also use something called pipeline parallelism, but PyTorch has kind of moved away from that in recent years, I've found. And the support for it isn't what it used to be. So, last thing I'll say is profile your code. If you don't profile your code, you won't know kind of what's going on. You won't be able to see how, even with DDP, how DDP is helping you, how you can optimize your training workflows better. With FSDP, it's essential for understanding what the trade-off you're getting between memory and communication. Because in this case, what we found with both our models is that it probably isn't worth it. But with other models, you might find something different, and you also need to optimize it to you need profiling to be able to optimize your throughput when you're talking about moving to a multi-GPU setup. So this talk will likely be, transformed into some documentation that will show up on the Alliance documentation, and that will be edited in progress as more details about. I can add more details about configuration possibilities, and kind of get into that and add activation, checkpointing, and all of the sorts of optimizations we can get into. So stay tuned for that. And you'll likely hear from me again at a future colloquia, getting even deeper into this topic. And with that, that's it I have for today. I'll be happy to take questions. I know the workflow from FSDP can be kind of confusing, how things are moving around as it's training. So feel free to put questions in the chat or unmute your mics and ask away.